Swayam Prabha. Digital India. Educated India.
Hello students, welcome back to the organ printing course. In the last few lectures, we have discussed what is bioprinting, what are the different types of bioprinting technologies available. Along with in great details, we have discussed all the different types of bioprinting technologies. In this lecture, we'll now compare different types of bioprinting technology available. Also, we'll compare the capabilities of different bioprinter types, right? So if you see in this table, I have listed the different properties, parameters of the bioprinting technologies, and also then we'll discuss different types of bioprinting technology like inkjet, extrusion, and laser assisted that we have already discussed in the earlier lectures, right? So we'll go one by one. So in terms of material viscosities, now we know what are the at this stage we know what are the different types of materials, or at least what are the different types of viscosities can be used for different types of bioprinters. During discussion of each of these technologies, I have discussed what kind of viscosities are good or viscosities are required for printing tissue structure with a particular type of bioprinter. So when you see viscosity, like material viscosity, then in case of inkjet printing works on the principle of droplet generation using either thermal or piezo based mechanism, right? So there mostly we use very low viscous material, and I have also mentioned that we use water like viscous material. So the viscosity in this case, in case of inkjet printing, is very low, and please remember this viscosity almost like water or buffer, that kind of viscous materials mostly we use. That's why there is also, I have pointed, there is a challenge of printing three-dimensional structures with this low viscous materials. So the viscosity in case of inkjet, the viscosity is low. Now coming to extrusion based bioprinter, there we can use low to moderate viscous, even high viscous material can also be used, right? So this technology, in extrusion based printing technology, here the very wide range of viscous material can be used, starting from very low viscous to high viscous materials can be used, because here the principle is we put the material into the syringe and then we apply pressure on the syringe. Either it can be a pneumatic pressure or it can be a mechanical pressure for extruding the material. So that's why in this case this printer is capable of extruding materials of different viscosities, starting from very low to very high. So this is like 30 MPa to almost 10 to the 7 MPa viscous. That much viscous material can be used. In case of laser assisted, from low to moderate viscous material we can use. Very high viscous materials cannot be used in case of laser assisted, because if you can recall the mechanism of this laser assisted bioprinting, we have seen there that it has a ribbon like structure. Then the top layer is the glass layer where the laser can pass through that, and then the energy absorbing metal layer where the laser can strike, and then the metal layer can get heated up, and then it gets heated up, and then the next layer is the bio-ink, and then when the laser hitting the gold metal layer, a bubble will be produced because of this high pressure gas that propel the droplets to generate, right? Or the droplets are dislodged by that high pressure gas. So that's why if you use very high viscous material, then there will be a problem of dislodging the material or this droplet generation, there will be a huge problem in the droplet generation. So that's why in case of laser assisted bioprinting, mostly we use low viscous material, low to moderate viscous like this viscous materials. Now we have also discussed the gelatin methods. Gelatin is important because it induces solidification of the printed material. That means in any of this printer, like when we extrude the either we extrude the material or generate droplets by any of this printing thing, that time the material is in the form of fluid, right? Then after the printing, that material should start solidifying. That's why because that solidification process enables shape retention of that printed structure. Suppose we are to print a particular structure, then if the material can solidify upon extrusion or upon printing, then that time the material can retain its shape. Otherwise, there will be a shape distortion. So the printing fidelity would be not that great. So that's why we need certain kind of gelatin, but most important thing is that we need biocompatible gelatin. But there are different types of gelatin mechanism exist like chemical gelatin or photo cross-linking, even different physical cross-linking like shear thinning, temperature induced cross-linking, all these things are there. So in this case we will see, like in case of inkjet, both chemical and photo cross-linking gelatin method can be possible, because when the material, suppose the material comes out as from the nozzle as droplets, at this stage, suppose if we introduce some cross-linking, like suppose the photo initiators are already mixed. So in case of, let me explain this photo cross-linking. In case of photo cross-linking, what happens? The material is mostly photo cross-linkable. That means photosensitive materials are mostly used, and then we also add some photo initiators. So photo initiators are the material that upon exposure to light that will initiate this cross-linking process. So photo cross-linking is very important for solidification process, and that process can also be very fast. Like, so photo cross-linking can be option. Chemical cross-linking is like when if we introduce, suppose after extruding these droplets are collected to a substrate where we introduce some cross linkers. So that cross linkers is that can go and bind to the material by chemical means. So that it induces some chemical cross linking. So both these things are possible with gel for inkjet. In case of extrusion, different types of cross linking, either it can be chemical, photo, shear thinning is another thing. Shear thinning means where upon increasing the shear rate, if the viscosity of the material comes down. So what happened? In case of extrusion, when we are extruding the material, basically we are applying some kind of force. So that due to the shear force, due to the high shear rate there during extrusion, the material viscosity comes down. So it helps in extruding the materials. But then when the material comes out of the nozzle, then there is no shear force. So that time the viscosity again goes up. So that helps in retention of the structure, retention of the line, retention of the structure in case of extrusion based bioprinting. So shear thinning material definitely helps in better shape retention. So that's why these materials are very popular or very good to be used as a biomaterials for extrusion based bioprinting. Similarly, temperature induced cross linking can be another thing. Suppose I use a material that has a temperature sensitivity. That means suppose let's take an example where suppose gelatin. Now gelatin, we know that gelatin has a critical transition temperature around 30 degrees centigrade. So above 30 degree it behaves like a fluidic material, but below 30 degree it behaves like a it's like a gel. Okay, so now what I can do, I can use this. So during printing I can maintain the temperature above 30 so that the material can easily come out. But after printing I can reduce the temperature, so I can reduce the temperature, or that means I can collect that on the stage at a lower temperature where the temperature can be maintained below 30 degrees Celsius. So that helps in again solidification of the gelatin material, gelatin biome. So similarly, like this, there are various different types of materials available. We can use them for this extrusion based bioprinting. Similarly, for laser assisted, either chemical or photo cross linking, both the things are possible here, because In inkjet and laser assisted, please note that in both these cases, because it's a nozzle free approach, that's why we don't have the advantage of using a shear thinning material in both these cases, right? But we can use any chemical cross linking or photo cross linking for laser assisted bioprinting and also for inkjet based bioprinting. So this is for gelation methods. We can use these different types of cross linking mechanism, and now you have a clear idea in which bioprinting technology, what kind of cross-link gelation methods can be applied. Now let's to the preparation time. Preparation time means here starting from the bioink preparation to the printing, all these things, right? To the generation of the CAD model, even the printing codes, everything, creating the codes, writing the codes, everything comes under this preparation time. So in case of inkjet, because the process is very simple, we don't have any very high preparation time. The bioink can be prepared very fast. Here bioink means mostly the cells or biomolecules, those are suspended or mixed with the media, right? And then can be directly used. So the preparation time is very less for inkjet printing. Here also the other thing doesn't take much time. But in case of extrusion based bioprinter, the preparation time is low to medium, because certain cases we need to prepare the biomaterials or the bioink, and that can take some time. So and then also we need to add big cells with this, so we need to take care of that process, because the cells are very sensitive. So when we mix with the material, then we also have to provide nutrition, oxygen all to the thing. So that can take some time, because we need to prepare the bioink, where suppose the cells are encapsulated in the hydrogen, then we'll add some media where nutrients are there, and then and also the oxygen is there. So those things. So the preparation time in case of extrusion bioprinting is medium. In case of laser assisted bioprinting, the preparation time is medium to high. What happens, if you can recall, in laser assisted bioprinting, one component is the ribbon. So ribbon, as we have already discussed, ribbon is a three layer thing, where the first layer is the glass, then then below the glass there is an energy absorbing layer or the metallic layer, then the bioink. So that ribbon has to be prepared in advance before the bioprinting process. So that's why it may take some time. So here in case of laser assisted bioprinting, the preparation time is medium to high. So other thing is also the whole process can take some time. So that's why this here it is medium to high. So please remember, in case of inkjet, because of the simplicity of the process, the preparation time is low. But in case of extrusion bioprinter, the bioink is the main ingredient here. So preparation of bioink, it may take some time. In case of laser assisted, we have to prepare the bioink. Also, we have to prepare the ribbon. So that may take some time. So that's why the preparation time is medium to high in the case of laser assisted bioprinting. Now coming to the print speed, definitely inkjet printing outperforms all other process, because in case of inkjet printing it's a high throughput process, because hundreds of droplets can be generated at a time. So that 10,000 droplets can be generated per second. So this process is very fast, right? So that's why, because the mechanism is such that in case of inkjet printer, we have discussed this, that there's in the printed there's a nozzle, so there's several nozzles. So multiple nozzles are lined up in the printed, and then at a time they can be filled, and the droplets can be generated at a time. So this is a very high throughput process. The droplet generation is very fast. In case of extrusion based printer, because the material has to be extruded through the nozzle, so the challenge is we cannot push the material very fast. Otherwise, what will be, that can lead to generation of shear stress. That shear stress can damage the cells. So this process is little slow, right? In extrusion based bioprinting, process is slow. So here like 10 to 50 micrometer per second. So that's only that much speed can be used for printing that structure, right? So in case of extrusion based printer, print speed is typically slow. Laser assisted, it can be medium to fast, because here also it's a contactless, non-contact approach, nozzle free approach. So that's why in this case also we can print very fast. It depending upon how the laser moving on the surface and how fast that those droplets can be generated. So here also this process can be medium to fast. So in terms of print speed, inkjet printing outperform all others. Resolution or droplet size, here also the inkjet printing again outperform all other printer types, because here also very fine droplets starting from 1 picoliter to 300 picoliter, that's it, like that much fine droplets can be generated, right? It also depends on the nozzle diameter, right? Most of the we have seen the nozzle diameter is around 50 micron. So that typically we can generate very fine droplets. That's why the resolution is very fine, and with these fine droplets we can create a very nice pattern of this different cellular constructs. That's why for cell patterning, inkjet printing is a very popular technique for cell patterning. For cell, also we have discussed this in our inkjet printing lecture, that where that's why inkjet printing is used for patterning cells, DNA, all other different types of things. In case of extrusion based bioprinting, here the resolution is directly dependent on the nozzle diameter, right? So if we can have nozzles of fine nozzles, then the resolution can be high. But if the nozzle size is more, then again the resolution will be compromised. But one important thing to remember here, though some nozzles of 5 micrometer nozzles are available, okay, but please remember the cell size is almost like 10 to 30 micron, anywhere between this, right? Different types of cells. That's why now we cannot use a nozzle lesser than even very close to the cellular dimensions, right? We have to have a nozzle size that is higher than cellular diameter. That's why typically 100 or more than 100 micro nozzles are used for bioprinting with extrusion based bioprinters. So the resolution is not that great like inkjet bioprinting, but definitely resolution is also, in this case, is good. Laser assisted, here also again the resolution is very high, very good, because here we can get a microscale resolution where we can generate droplets containing single cells. So that much fine resolution can be made. So that's why this again laser assisted bioprinting technique. Yeah, this also the resolution is very good. Resolution is very good in case of laser assisted bioprinting, and that's why with this kind of bioprinters, even with inkjet similar to inkjet based bioprinting, we can generate droplets containing single cells, and then those single cells can be patterned as per the requirement, and we can create a very nice multicellular architecture of a particular tissue, right? So that's why these two printing technologies are very good of this thing. Now coming to the cell viability, because these two, inkjet printing and laser assisted, both are nozzle free approach, non-contact based approach, so the cell viability is very good. Though in case of inkjet printing there is some concern about the generation of heat, but if you can take care of the parameters, definitely that heat cannot be that much damaging to the cells. So we can get very good cell viability, like more than 85% cells can be viable. And in case of laser assisted, also similar thing, if you can take care of the laser intensity and the duration, then definitely you can get a very good cell viability, 95%. But in case of extrusion based bioprinting, actually as per the literature, a wide range of viability people have seen, like starting from 40 to 80% cells are viable and depending upon the parameters being used. But if you can take care of the parameters, then you can get very good cell viability with extrusion based bioprinter also, right? Now cell densities are in the bioink, how many cells are, suppose what is the density of cells, so how many cells are loaded in per ml of bioink, suppose. So in case of inkjet, the cell density cannot be very high, so it is low cell density can be used, like 10 million cells per ml can be very well used for inkjet based bioprinting, because we have seen that in case of inkjet there is a nozzle, and that through the nozzle only we are generating these droplets. So if we increase the cell density, then there can be a problem in nozzle clogging. So that's why we cannot use very high cell density. Other than that, there is another problem in case of inkjet thing. The cells can settle down on the nozzle and that can clog them. So that's why very high cell density is not advisable. in case of inkjet based bioprinting, but extrusion based bioprinting very high cell density cap, because this process we use some hydrogel, some biomaterials to encapsulate the cells. So that's why we can use very high cell density, and there's not much problem of nozzle clogging if we can homogeneously disperse the cells within the bioink. Even another possibility is, because if you can use higher dimensions nozzle, higher dimensions syringe or nozzles, then cell spheroid can also be printed. That is another important thing in this extrusion based bioprinting. We can even print cell spheroid. Cell spheroid means when the cells are clustered together in a round shape, that we generally call as cell spheroids. So typically the spheroid dimension is anyhow between 50 to 400 microns, but mostly people use 100 to 200 micron spheroids are mostly used for bioprinting applications, and that time again the nozzle dimension has to be around more than that spheroid size. So that is another thing. So cell spheroid densities can be very high in case of extrusion based bioprinting. Now in case of laser assisted bioprinting, again the cell density can be medium, like almost like 100 million cells can be possible per ml of bioink. So here also the cell density can be high, but moderate to high cell density can be caused here, because it's a nozzle free approach, and we can load the cells, we can load the material within the load the cells within the bioink, and then the droplets can be generated, so this can be used. Now in terms of cell density, inkjet typically is low cell density can be used. Laser assisted medium to high density can be used. In case of extrusion, a wide range of cell densities starting from low to high can be used. Even cell spheroids can also be printed with extrusion based bioprinting. Now coming to the printer cost. In inkjet bioprinting, the cost of the printer is very low. As I have already discussed, the common office printers are used or modified to print cells. So the cost of the printer is not very high in case of inkjet based bioprinting. But in case of extrusion bioprinting, the cost of the printer can be medium to high, because there are extrusion there are printed movement controller, there are material dispensing controller, all these different things are there. So that's why the medium price. In case of laser, because of the laser is expensive, again the ribbon, all these things, the whole setup is expensive, so that's why the cost of the printer is very high in case of laser assisted bioprinting. Let's see the advantages and disadvantages of different bioprinting techniques. We have discussed some of these things in our respective bioprinting technique, but let us have a comparison of different advantages and disadvantages for all three techniques, like inkjet, laser assisted, and extrusion based bioprinting. In terms of, let us first talk about the advantages of these three techniques. Like inkjet based technique, we have seen that we can generate droplets of very fine, that is the first point anyway, but here low heat effect, that is the another advantage. In this case there is not much heat generation, though in thermal based inkjet printing there can be sometimes the heat can be generated, but there is not much heat generation. Electronic control of drop size and ejection rate, that is very important. We can control the size of the droplets in case of inkjet printing and their ejection rate, so those things are very much controlled. So that's why it's an advantage. So we have a control over the how much fine droplets can be generated and what rate we can reproduce that, so that we can create a pattern of particular drop size and particular rate of particular ejection rate. So this is the advantage of inkjet printing. In case of laser assisted bioprinting, because here mostly we use a biomaterial of low to moderate viscous, so that biomaterial is coated in the ribbon, right? So that's why we can use wide range of materials can be used for this kind of thing. So there is the material, because the material as such there is not much challenge with material selection in case of laser assisted bioprinting, and it's a nozzle free printer setup, so that helps various ways. One thing is there is no problem of nozzle clogging. Other thing is the droplets can be also here also we can create a verified droplets. So that's why microscale resolution is another advantage of this bioprinting technique. Here also, because of this microscale resolution, we can create very fine droplets and that can be printed. So these are the advantages of laser assisted. In case of extrusion, again, wide range of material choice. So we can use any type of material. The only thing is we have to have a low to moderate or very high viscosity is a range. And in case of extrusion printed, because we can use various ranges of viscosities we can use. So that's why various types of materials can be used. But when you are using for bioprinting, please remember we need to use materials that is aqueous based, because we also incorporate cells within this bioink. So that is one important thing to remember. Slightly viscous bioink can also be used. So in this case, because we are extruding the material, so that's why slightly viscous bioink also can be used. That's another advantage. And we can print tissues with very high cell density. That's a major advantage of extrusion based bioprinting, because certain cases in our tissue, if you see in the native tissue, cell density is typically very high. Also it differs from tissue to tissue, but typically the cell density is high. So to mimic that kind of native cell density, we need to print at a very high cell density, right? So that's why in extrusion based printer, that is the advantages. We can print a high cell density structure. Another thing, we can also print vascular tissue construct. That is another advantage of extrusion based printer, because we can print a vascular construct. Tissue construct can also be printed, and people have shown that the possibility of printing vascular tissue construct with extrusion. In one lecture, I will discuss how the vascular tissue constructs are printed, targeted with different types of bioprinting technologies. So there we will discuss in great detail. Other thing is the structure printed with extrusion based printer, it has very good mechanical properties, unlike other two like inkjet based and laser assisted, because you know that in both the cases it is like the droplets. With the droplets we are creating the structures, but in this case actually we are extruding a viscous material, and that material comes out in the form of filament. Though whatever the structures we print, it has good mechanical properties. Now coming to the disadvantage, in case of inkjet printed, limited choice of materials are available, because we need to have the material that is we need to use material that has low viscosity. So there is limited choice of materials available. Other thing is limited height. You know that, because I have also discussed this earlier thing, that with a very low viscous material we cannot make a three-dimensional structures, because if we put a drop on the stage or on the preceding drop, then it will collapse or it will just slide away. So I cannot create a three-dimensional structures with this extrusion based with inkjet based bioprinting, unless I use some support material, support structure like biopaper or something. High viscous bioink cannot be used, because then this droplet generation, there will be major problem in droplet generation, and also there can be a nozzle clogging and other things. So high viscous materials cannot be used in case of inkjet. That is the disadvantage of this inkjet based bioprinting. Difficulties in complex 3D geometries. So again, complex 3D geometry for patterning in 2D surface, creating very nice very complex pattern can also be created in 2D surface, but creating complex geometry, 3D geometry is a challenge in case of inkjet based. When the structure made with this kind of inkjet based bioprinting, they have typically poor mechanical property. Mechanical property is not that great. In case of laser assisted, the major disadvantage is the equipment is very expensive. So this is not high, it's not very affordable. So affordability is a concern when it comes to inkjet based bioprinting. Other advantage is the heat effects, right? So when in case of laser assisted bioprinter, because we are using laser and we are hitting the surface, we are hitting the laser passing through the glass layer, hitting the metal layer, right? Basically it heats up. So for very fraction of time also, the metal layer heats up. The temperature increases tremendously, and that's why that heat can be dissipated to the bioink, and that bioink, there can be a detrimental effect on the bioink because of that heat, generated heat. So that can be a disadvantage for laser assisted bioprinting. Now in case of extrusion based bioprinting, the disadvantage like the viscosity and temperature of the material is a thing, because in this extrusion based bioprinter we have to have certain viscous. We cannot use very low viscous materials, and also we cannot use very high viscous materials. So we have to have a viscosity that in the in between range where that can be very well used. Other thing, temperature of the material, we cannot use a temperature very high temperature material. So that can be also another thing. Now cell viability can be affected because of the extrusion pressure. Now when we apply pressure on the, in case of extrusion based bioprinting, we apply pressure, either it can be pneumatic or it can be piston driven pressure, mechanical pressure. So that can cause shear stress. That shear stress can get generated at the nozzle. That shear stress in turn can damage. So cells can get damaged due to the shear stress. So that is can be one challenging part. So that's why we need to optimize the process parameters so that the generated shear stress is less. Now, when low viscous bioink is difficulty in operating complex shapes. So, if we use low viscous bioink, because the low viscous bioink also we can use for extrusion bioprinting, when the viscous coming out, there the printed filament generally collapse due to the low viscosity of the material that cannot hold itself. So that's what will happen. That will collapse. So we cannot create a very complex shapes with this low viscous bioink. So that is one challenging in case of extrusion based bioprinting. So these are the advantages and disadvantages of these three bioprinting techniques.